Much better. Okay. So thank you, Thorsten, for having given us already some good introduction to the pros and cons of deep neural network. So this topic will be as well on neural networks, a little bit also on machine learnings. If we come back to the innovations, the ideas that brought us to review a little bit the workflows we had so far for image segmentation, I would say that three of the main reasons could be devised as the fact that we have a prevalence of segmentation in many of the workflows. So the idea of having a very good segmentation process is quite neat, because afterwards you can guarantee that all the rest of the workflows will be quite smooth. So tackling the problem of segmentation could be already a good starting point for many of the image analysis that you have to perform. Second is that we are all concerned by this big data problem. And you heard it today, that all these big data go naturally with fully automated methods. It's no longer any option to fill there manually in order to annotate your data. And on top of that, you would like to have robust algorithms that cope with the variability that is inherent to the biomedical imaging. And possibly also you would like to have these algorithms to be as accurate as possible. Okay. Last but not least, all these current automated methods that you might have on the shelf are very often application specific. So if you take them and you try them out in your data, most probably they are not going to work. You will have to work a little bit on parameters, on pre-processing in order to make them work. Or they fail due to intrinsic algorithmic limitations. So simply because your algorithm is based on some heuristics that have its own limitation, or maybe because the algorithmic is too complex, and so all the computation process is too long. Okay, so you would like to find another solution for that. So looking at image segmentation, naturally we had our look to the state of the art at the moment, which is, you heard Thorsten, it's actually deep networks that completely challenge this task. And oops, this is okay. Nice. Okay, so I had a plan B. Where do I have yours? Okay. Good. Okay, so this was my plan B here, in case it wasn't opening. I wanted just to show you what these people do here. So here it's about full resolution, so images with high resolution and recursive networks. So you can see here, for instance, that you have a very accurate segmentation, very sharp. You see certain level of abstraction already in this image, because you have different types of layers. You have the pavements, the roads, people, signs, the cars. It's not able to distinguish the the mark of the author, but you certainly do. So this is a bit the state of the art in what we call here semantic segmentation, because it, so I will close this. So now the question is, how do we leverage the power of deep learning? Because this is absolutely amazing. You can imagine that you can put a label to any type of abstract object in your scenery, and this would be great so, but many questions are still open. So Thorsten already talked about it. It's a main problem in deep architectures. What about the ground truth? Okay, do we have them? How do we acquire them? And how many are necessary? So we know that generally deep architectures get better and better with the amount of training data. And so the question is always, how many do I have to have in order to get a sufficiently accurate model? And then the key question, who is going to annotate this data? Yeah, that's a big problem. And then we have problems or issues that are specific to the biomedical, but not completely. For instance, we have in the cellular mechanism some rare phenotypes. How do we deal with these rare phenotypes? Are we going to just cope with this rarity, or are we going to use data augmentation? And if we use data augmentation, which kind of augmentation are we going to use? Yeah. So in order to make use of all these technological advances in computer vision, but without going into the drawbacks of deep architectures, the approach that we chose was still to keep the neural networks to make a supervised learning, because neural networks are the horsepower of deep learning. So certainly they are there for something, right? It's I admit a basic, naive, and risky assumptions, but you will see later on that neural networks have been studied in the past, and there are some reasons why they are efficient in computer vision. Second difference with deep learning is that we will still keep handcrafted features, and we will not rely on convolutional layers as it is done standard-wise to discover which are the features of interest for your classification. Then, if we use these handcrafted features, we would like to speed them up in order to have very fast feature calculations and inference calculations, and these we will use for that GPU computations. And another trick that we will use as well in order to speed up all the inference time is to reduce the feature space. This is done in a semi-automated way in our workflows. And last but not least, the fundamental question of the annotation of the ground truth. This is made using Elastic, the annotation tool, which is fast and user-friendly. But we only use the interface. We don't use the random forest classifier that is provided. Okay, we just use the labels, and then we model our own feed-forward backpropagation neural networks on these labels. Oh no, come on. Okay. Do I get some extra time because it's bugging? No? Okay. What is this mine? No, this one? Oh, shit. Okay, and so, oh, come on. Huh? Can we maybe copy it here on the drive? Yeah, this will go always maybe.
Okay, run it from there.
Yeah. Okay, we stayed. Hmm?
Is there a link in the slide?
Yeah, but I copied everything here on the. Hmm? Sorry? Ouais, ouais. Tu crois que c'est ça? Enable. Okay. Ta-da. No. Okay, good. So I think we are going to do something like this. Yeah, I can, yeah. Okay. So the next minutes will be about giving you a bit more details on the various projects we are running using these workflows. So it's a bit a pity because there are many videos. Okay, so I said before that it was a bit naive to use or just to assume that neural networks are going to just fit for our needs here. Albeit, as I said, there are many works that have been realized and performed in the past that gives us good reasons to use GPU computations. So first of all, on neural networks, very often you have features and inference that are computable on GPU and multi-CPU. And just to give you an insight here, so what I did is to calculate a very classical feature that is called the Hessian of Gaussian eigenvalues. These texture features are very often used to, for instance, if you want to extract vessels in an image, okay, for instance, if we see here a series of these eigenvalues calculated on the mouse here, you see that it peaks quite nicely at the tail here. So meaning that every time you have a tube, okay, it will give you the directions of the highest variations of the gradient. Also for cells, it's a very good feature for the calculation of the boundaries that is used actually. And now what we did is, so you imagine for every pixel of your image in 3D, you have to calculate this 3x3 matrix, which corresponds to the second derivatives, and then you calculate the eigenvalues. So it's a quite intense computation. And so we did it on multiple images, 3D images of n by n by 64 pixels, okay? And that's the result when running it on a GPU, GTX 1080, and on CPUs. So here with a very small kernel size of sigma 1, Windows size 7, you have already between the CPU and the GPU a speed-up factor of roughly 10 to 15. If we go now to larger kernel sizes, so something that is quite consequence, sigma 5. Here we have speed up of almost 250 for certain grid size of 512 by 512 by 64. So this is quite a lot. A second benefit of using neural networks is that when you use these feature space reduction, you get a natural regularization. So neural networks are known to work quite well and to be stable with a large amount of features, but here they show as well that they can be quite robust against overfitting when you reduce also the features. And last but not least, they also enable fast training or retraining time. So if we look at this diagram here, we have the prediction speed that is quite fast here for this ensemble of neural networks here compared to complex trees. And the accuracy as well is one of the best when you compare it to other types of machine learnings. So now we will step to some examples. Here we have a single mouse here that is running over. These are typical applications that we do for low-level feature extraction. So we just care about being able to extract the blobs, the intensity corresponding to the body of the mouse. And we analyze the different features extracted from the trajectory. Here the mouse is cabled, so we gather all the information about the speed on different timestamps. Here we can see by summing up the values of the different experiments that we have and an overactivity of the motor circuits during the laser on. You can even work with the different trajectories and look what is happening before the laser on, during. So during would be this long blue line, so meaning that he's really activating his motility. And then you have some latency afterwards. So this gives you quite a rich door to analyzing all the data that you might get out of that. In a bit more abstracted level, we can also do more complicated things on these videos. So for instance, on the left here, what we have done is we have labeled not only the body of the mouse, but also the skin and some parts of the head where the mouse is cabled. And here in this experiment, what was seeked was the relative speed of the mouse. So this mouse was modified so that when it got the stimulation, it was running backwards. Okay? In order to be able to say that the mouse is running backwards, you have to know where the tail and where the head is, so that you get the sense of this natural orientation. And then whenever you had dot product between the displacement and the direction vector of your mouse, and this cosine was positive, then it means that the speed was negative. Okay? And then again, you reproduce all these measurements of the speed during the laser on periods, and you can assess different types of patterns in the trajectory, whether you are changing parameters of the laser, for instance, in this case. On these other experiments, we had a mouse on a rotarod, and the person was interested in analyzing the movement of the pores, okay, that were here labeled in blue. It's not a big deal once you have, so here you still see that they are labeled within the same label, so just pore. You don't know if it's a left or a right pore, but this can be extracted afterwards, and what you see here is the movement of the body in black, and then you have the two separated movements of the left pore and the right pore in red and blue. So for instance here, what we see, we don't have the animation anymore, that's a pity again, but what we see here is that you don't have completely asynchronous movements. It's more like it's hopping, okay? So you have one pore that is lifting and immediately after the other one that is joining. Other types of experiments, this time for our behavior classification for the Duality group. Again, we have different types of movies that were acquired. Here the challenge was to show that within one model you can deal with different types of backgrounds, and even you can deal with problems such as the occlusion, because here, for instance, in these two videos you have the cable that sometimes go on top of the mouse, but still you can still, you can show that you can still properly detect the mouse. Once you have all the trajectories, you can input them and you calculate further features that were used in a behavior classifier called JABA for the Janelia Automatic Animal Behavior Annotator. And within this, you annotate different types of behavior, and you have an automatic prediction of your behavior detector. A bit like in Elastic, but for behavior classification. Here as well, we have some type of behavior analysis, but this time it's done within another program that is called Celeste, which is specially dedicated to the analysis of C. elegans. So here we showed that these big movies were also a challenge, because here this time on 2D you have to calculate your features on larger images than simple movies, where the feature reductions just really plays a role here. So you extract a kind of a binary mask, which is quite appropriate in order to have the guarantee that you will go through the tracking module and the measurement computations. Here what we see, and this is one of the major interests here, is to analyze the way the C. elegans is swimming. And so the white codes when the C. elegans is completely straight. When it's curled clockwise, it's in red, and when it's curled counterclockwise, it's in blue. Of course, in order to be able to tell the counterclockwise or clockwise, you have to know where the head and the tail as well. So these are also the kind of things that you can do with your machine learning.
Raphael, you
yeah.
have to switch to the conclusion.
Okay, no problem. So here we had some other behavior science example with zebrafish. Here with quantitative biology, where we show that these workflows work on blastocysts for the segmentation of the nuclei, for the counting and quantification of neural rosette as well, and on organoids, where the main challenge is to be able to separate with a watershed the different nuclei. In concluding remarks, we have seen so far that neural networks are perfectly adapted to the problems we had to solve. First, because they are accurate. Okay, we have a very accurate segmentation of your object, so you can track it error-free. And because they are fast. Okay. The next steps are that we will have a look at deep learning, UNet especially, but also the possibility of using transfer learning, because you get rid of the burden of getting your ground truth. And we'll also have a look at the full CUDA versions of our 3D features that should further speed up the calculations. And I just shortly spoke about, for the case of the organoids, we also working on learning a seeded watershed, which should be more powerful than the heuristic methods we have that are still a kind of agglomerative watershed. Okay, so I think that's the last one. Thank you for your attention, and it's open for questions.